Hi, I'm Teacher Thomas. Welcome to A-Level Maths. This is 9231 Further Probability and Statistics. Topic 3 chi-squared tests. November 18, 2021 paper. Question 11b. A machine is used to produce metal rods. When the machine is working efficiently, the lengths, x centimeters, of the rods have a normal distribution with mean 150 centimeters and standard deviation 1.2 centimeters. The machine is checked regularly by taking random samples of 200 rods. The latest results are shown in the following table. As a first check, the sample is used to calculate an estimate for the mean. Requirement 1, show that an estimate for the mean from this sample is close to 150 centimeters. To find my estimated mean, I take the midpoint of each interval and multiply by the related frequency. So I'll have, for my first category, 146.5 as a midpoint, times 1, plus on to 147.5 midpoint, times 2, plus 148.5 times 23, plus 149.5 times 52, and I'll go ahead and write up the other four calculations. Here they are. When I sum these 8 products, I arrive at 30,064. I divide by 200 the sample size, which gives me 150.32 centimeters, which shows that the mean from this sample is close to 150 centimeters. Continuing to requirement 2, as a second check, the results are tested for goodness of fit of the normal distribution with mean 150 centimeters and standard deviation 1.2 centimeters. The relevant expected frequencies found using the normal distribution function are shown in the following table. Requirement 2, show how the expected frequency for 151 to 152 is obtained. I'm going to sketch a curve that represents what it is that I'm looking for probability-wise. This isn't a part of the requirements, but it helps me to conceptualize. The mean given is 150, and we're looking for the range 151 to 152. And this shaded region represents the probability that relates to what we're looking for. To work with the normal distribution function table referenced in the question that's in the formula book, this says MF10. Currently the formula book is MF19. I need z-scores. So let's find the z-score for the measurement of 152. That will be the measurement, 152, minus the mean, 150, over the standard deviation, given as 1.2. Be careful to note that the metric we're given is standard deviation. Sometimes you're given variance. If so, you need to take the square root of the variance to get your standard deviation for the denominator. The resulting value is 1.667. And when I look up using the table phi of 1.667, here going from the z to the probability, I work around the edge of the table and go in to find the relevant probability. I find 0.9522. That's cumulative all the way up to 152. What I want is, I don't want to start at the infinitely low end. I want to start at 151. So now I'm going to similarly find the z based on a measurement of 151. 151 minus the mean of 150 over standard deviation of 1.2. This gives me 0.833, and the resulting lookup gives me a probability 0.7975. And now the probability represented by the shading is 0.833 minus 0.7975. And I want to relate this to an expected frequency, so I will multiply by sample size of 200. So when I have sample size of 200, this probability results in a value of 30.94. And notice up in the table, 30.94 is the expected frequency that they have for 151 to 152. Now on to requirement 3, test at the 5% significance level the goodness of fit of the normal distribution to the results. I'll start with hypotheses, the null, and the alternative. The variable with a normal distribution of 150 and 1.2 squared is a good fit. And rather than using the notation, you could write that out in some way in English as well. Or it is not a good fit. I want to calculate my chi-squared statistic. To do that, I'm going to need to compare observed values and estimated values, and I need to know how many categories I'm working with. So if I go back to where I have expected values, I observe looking for any expectation less than 5, I see 2. I'm going to mark these in red. The very first category and the very last category. So what I want to do is I want to combine both the observations in the first category and the expectations in the first category, and the first two categories, excuse me, and then going down to do the same for the final two categories. Note we're going to consolidate each of these into one category. So at the front, those first two will be one category. At the end, those last two will be one category. The consolidation is because the expected value, not the observed value, we're looking at the expected value. Because the expected value in each case is less than 5, we're going to consolidate. So once we consolidate, we're going to have 1, 2, 3, 4, 5, 6 total categories. 1, 2, 3, 4, 5, 6. I'll bring over my observed and expected values, and then we'll work on calculating the test statistic. These are my data for my chi-squared statistic. I want to evaluate my observed minus my expected value quantity squared over my expected value. I'll describe step by step the first calculation and then post the others. Observed of 3 minus expected of 9.56. That gives me 6.56, or negative 6.56. I square that value, then I divide by 9.56, and I get 4.501. I'll post the remaining 5 calculations now. These are the additional calculations. As a reminder, I'm going to go back up and box the first category measurements. This is simply a reference to the fact these are combined. This isn't a notation of any sort that it would be required in the paper. I simply, as a reminder, am putting those in boxes because previously I combined the first 2 categories and the last 2 categories. Okay, so that's my reference to those consolidations. Now what I want is to sum these values I've calculated as O minus E quantity squared over E. The sum gives me my chi-squared test statistic. That is 15.619. For my critical value, I want to determine degrees of freedom. Here I have consolidated to 6 categories, minus 1 as a standard adjustment, minus the number of estimated parameters. We don't have any estimated parameters here. We were given the standard deviation and we were given the mean, minus 0, 5. So we want a critical value of chi-squared with 5 degrees of freedom. The requirement is a 5% significance level. We will use 0.95. And we get 11.07. With the test statistic and the critical value, I can compare. 15.619 is greater than 11.07. The test statistic is greater than the critical value, therefore I reject the null hypothesis. Looking up at the top, what's my alternative hypothesis? That's what I'm going to state as a conclusion or an explanation of my rejection. Applying the normal distribution to the variable with a mean of 150 and a variance of 1.2 squared is not a good fit. This completes the requirements for question 11b.